All right, we'll begin now. I'm Vivek Sharma from Dawen, Shen. We're here representing the Bioengineering department to present our senior design project on a low-cost automated liquid handling platform. So just to introduce you what we're going to be going over, we'll introduce the concept of liquid handling, explain it in some detail, go over our goals of our project, and then work through our process of design, the evaluation, show you a quick product demonstration, and go over some costs and budgeting and make some concluding remarks. So this brings up the question of what is liquid handling? It's essentially the key task in any wet laboratory work. And at its basic, it's transferring liquid from one point to another to perform a reaction and experiment. And you can use liquid handling to apply for experiments such as drug discovery, whether that's in a small academic lab or a big pharmaceutical company. Gene sequencing, so automating medicine, automated gene sequencing for medical applications, as well as academic studies, protein expression studies, anything that's done in a wet laboratory. And how is that commonly done today? It's done using the manual adjustable pipette shown here. So the user turns in a dial on the pipette to select a volume to transfer, loads a clear plastic disposable tip, as shown here, which is a key part of the process. And then, using your thumb, you activate a plunger to either aspirate liquid from a vessel or dispense it, as shown here. What are some problems with this? First off, the adjustable pipette was invented almost over half a century ago. So there's issues with they lose their calibration over time, they're inaccurate. And you're combining that with human error. So whether you depress that plunger fully, whether you get tired over a 3-hour experiment and you pipette differently over time, that's a problem. How is that solved in industry today is that they apply robotics and automation technologies to this liquid handling. And what does that look like? On your left here is a system sold by Eppendorf, which sells for about $45,000 retail. And as you can see, there's a limited workspace. Those are 4 microplates shown there, which are about this big. So it's a desktop-sized machine. On the right is a system made by TCAN and retails for $150,000 to $200,000 depending on your feature set. It can perform larger experiments, but there's a weight, size, cost restrictions on that. So how are we going to address those problems? First, we're going to reduce the cost. How? Implementing motion systems and motion control that are commonly available on the low-cost market. Secondly, we want to design our system with scalability in mind, from small academic labs to systems that are applicable in pharmaceutical industry. We also want to develop an intuitive and really effective software that can not only take commands in the user in an easy way, but optimize their experiments, reduce the amount of time it takes them to run a given process. So that results in our key architecture of our system, a hardware and software approach. Hardware consisting of this motion system, which can move our liquid transfer apparatus at any given position in 3 axes on our workspace. A liquid transfer system that will actually move liquid between the 2 points. And then from a software perspective, a backend that will control the hardware, a optimization, a logical system that will take user commands and reduce their time of experimentation, and a user interface that improves on some of the flaws available in current commercial softwares.
So to accomplish some of the things Vivek just mentioned, we needed to design hardware with 2 major requirements: a 3-axis motion system with a liquid transfer capacity. So a 3-axis motion system essentially consists of 3 independent motors, which allows for movement in the X, the Y, and finally the Z direction. And this allows motioning of our positioning of our pipette to any point within the workspace. Our pipette, again, needs to be able to accurately and reliably dispense a specified liquid to any location. So the first design consideration, which we deemed was most important, was speed. Given that time and cost are 2 of the major factors in evaluating the success of our system, we wanted our liquid handling system to be able to match those of low-end systems currently on the market, while not necessarily being as high as those offered at the high end of the price range. We were actually able to exceed some of these a median value, which essentially translates into practical application of crossing a microplate in 1.1 seconds or the entire gantry in 6. So in order to ensure accurate pipetting of liquid, we implemented an electronic pipette system. This was able to pipette typical volumes between 1 and 200 microliters with less than 4% error.
And keep in mind, these are very small volumes, almost droplet size or less.
So once we had a liquid accuracy, we also wanted to implement a motion accuracy. This is important because these 96-well microplates are very small. And so in order to position our pipette accurately, we made use of an encoder system. This allowed us to position the pipette head, as you can see in the video, within a single well from the plate, even over 500 repetitions. And finally, our last design consideration was the ability to detect tips and accurately measure liquid height. In order to do this, we chose to use iron-coated pipette tips. These are different from the more commonly used clear plastic ones. And this is because with the presence of iron, we're able to use our pipette to detect conductivity values. And that being the conductivity of contact with open air, the pipette tip, or liquid are distinctly different. And the system is able to use that to determine whether or not a tip has successfully loaded. The loading and ejection of tips is important to prevent cross-contamination. Whenever you're working with two different liquids, you ideally want to switch tips in between to avoid the issue of contamination. So that's some of the hardware of our system. We'd also like to take you through the software, which works behind the scenes to ensure the optimal function of our liquid handler. So current systems on the market currently ask the user to input what we like to call low-level commands. Low-level commands are commands such as, move from point A to B, pick up a tip at point B, and then move from point B to point C and dispense, and etc. What our system does is actually takes it 2 steps further. Instead, you can just specify a high-level conceptual command, which would be something like transfer liquid from A to B. So as you can see above, we ask the user to input 2 things. First of all is the high-level inputs, which again are concepts such as just transfer from where to where with a certain amount. And the second is a list of reagents that you currently have placed on the deck. Because our handler isn't completely autonomous, you still need to tell it what it has available to use. Finally, our software then takes those commands and will optimize it to reduce downtime and calculate the most efficient path to complete the experiment.
That one just took you through the back end. What's going on behind the scenes? What's going on in the front where the user actually interfaces with our software is this screen is shown here, which gives us a status and information of our system in real time. A key point that a lot of the people in industry like is verbose logging. What did the system do? Where did it transfer my sample to? We have that right here. We accurately record every single action of our system. We provide the user with information about the status of each of our axes, X, Y, and Z, in real time over here, and positional information above, and information about our pipetting system. How much is in our tip? Do we have a tip loaded? Are we sensing liquid? And just to show you that interaction in real time, the user is going in here and selecting to start a run. Logging starts immediately over here, and as you can see, the gauges and system information are updating in real time as the run is performing. And a key point here is that the user is easily able to see when and where an error occurs. And just what does an experiment look like on our system? We're running a short video here of our system lifting a tip out of a reservoir, moving along its y-axis here, and dispensing that disposable tip in a waste container before it goes and gets a new tip. It can also move along its x-axis here, or z-axis vertically right there. And what does an actual full experiment look like? The system is coming in from the top right of your screen, and it's loading a tip. We mentioned the system has to be able to accurately load these tips. It detects that one was not loaded, it'll successfully go and mate to a tip. And we're doing a 3x time lapse here roughly, and we're transferring liquid from an open reservoir into this 96-well microplate from also small tubes in the back there, as you can see right now. And the system is transferring liquid. As you can see, the colors are changing in the wells as we go. So how does this relate to cost? We mentioned some systems are expensive, right? The TCAN was a quite pricey system. That comes in at around $150,000 on average, give or take, with some additional features. Beckman Biomech 4000, that comes in around $75,000, And that's a medium footprint size system about the size of that table over there. The Eppendorf EP Motion, which is that 4-plate system we showed you on the first few slides, comes in around $45,000. You think, where do we come in? We got in under over $9,000. And we know that that's a prototyping cost. Commercial costs, retail values, slightly different. We can address that in a bit. What was the most expensive components? The motion control right there, $5,000. This is our XYZ positioning system. And that price is really dependent on the speeds you need. So we actually are scalable in that regards. You can use slower speeds. We can reduce your costs. The actual motion control software, so the logical back end, the power drivers were also quite pricey at around $2,000. And the electronic pipette, the system that performs the actual liquid transfers, was also at about $1,700. So on average, give or take some changes to our system we made, we came in around $9,300. And where can we improve in the future? The first thing that we want to improve on, not only in our system, because it's a known problem in commercial systems, is error handling. We want to be able the system to realize when it can recover from errors that it can say if it lost its tip. That's something the system can go and get a new disposable tip without user interaction, versus the system fell over on its side because someone hit it. The system can maybe send the user a text message or email to notify of a problem. We also want to implement microplate movement, the ability to move these test plates at different locations on the deck, so you can increase your experimental variability in that sense. And also integrate this automatic plate location system. So you put a plate on the deck of the machine. The way it is now, you have to calibrate the system to that plate. What if we had an image analysis system that could image the deck and automatically self-calibrate those vessels on our workspace? So just to conclude here, I want to say thank you to all of our companies listed here. They provided us some discounts, some free parts, and some of them are actually local companies, as well as the University of Pennsylvania, Department of Bioengineering, several who's in our audience, the BE Lab Director, and Dr. Rizk and Dr. Winkelstein in the back as well. And at that point, I'm going to open the floor for any questions. If you have any further questions after the end, feel free to email either of us.
If you had announced that you were a mechanical engineer and you were a mechanical engineering project,
This is a
I'm just wondering how close, I mean, some of the work you're doing seems very closely integrated with mechanical engineering also.
It is.
Is that typical? Is that what's happening?
It is. It's really applying mechanical engineering to biology. It's bringing this robotics technology to something, to a industry and a science that's traditionally avoided traditional engineering approaches to solving problems. So in that sense, there is a very strong mechanical engineering aspect to this.
How do you calibrate the system now? Do you program the positioning of things correctly?
So the system has a 3-axis vector space that self-calibrates. So it hits limit switches to know what are my bounds on our system. And to actually tell it where a plate is right now, we have a calibration tip that goes on, and the user would say, click on, I'm calibrating well 1, and I'm calibrating well 96. So these are 96 well plates, and we interpolate all the other wells. And we can do that for various plates. Any other questions? Or?